very kind introduction. Yeah, okay. Uh, well, I'm supposed to give a tutorial on actually, um, and so just to emphasize, like, the point of tutorials is like for someone who knows nothing about this subject to get something out of it. And so the basic difficulty you run into is like when the person giving the talk knows something about the subject, the question of kind of getting it at the right level. So basically, I really need people to ask questions if like something doesn't make sense, and I'll try not to be rude and dismissive. uh, yeah, so maybe I think uh, let me just say a few orienting words about where these things come from and what role you should expect them to play in subsequent talks. Okay. Um, and so here's a very basic idea, sort of like to construct objects with B modules from 1G, there's kind of there's three kind of basic views. One is kind of Eisenstein series and parabolic conduction. Two is we thought in the very last slide in the Poincare series. Let's see that. Okay. And the idea is that so there's going to be some third way to produce D modules above G, which is kind of you think of Kac-Moody local. And the first approximation, this is a tool you have in the geometric, in the Dhillon case, that you don't have in the normal period problem. Okay. So that's kind of just one of the fun special things we're looking at. So, cool. And so having said that, now let me give some purely classical motivation for what you want out of Kac-Moody workflow. So here's kind of the classical picture. So if you recall, we kind of have the upper half plane. So it's X and Y, or real numbers, and Y is greater than 0. And for modular forms, modular functions, the most classical ones live here, right? And so if you're kind of a geometer who actually thinks about lengths and angles, so you recall the kind of like this thing, it has it's like not the most standard metric, it's something where something happens with Y dependence. And related to that, it's kind of there's a certain so on any Riemannian manifold, there's a beautiful differential operator with a Clausian. Which in this case is explicitly the following thing. Okay, and in fact, let me just even by proportional to, I'm not worry about this type of thing. And the idea is that This creature plays a basic role in classical theory. Modular function. So the idea is kind of like Laplacian sort of plays well. The modular function instead. And so the type of thing you might sort of have in mind is that if you take an Eisenstein series, but this is all just kind of motivation, so you don't know precise definition, definitely don't need to follow this discussion. And the point is that when you take one of these things and you hit it with the Laplacian, well, okay, let me say equals. The whole point is that like you take a special function and you hit it with a Laplacian, and it just gets restored. Okay. And then for people who know these types of things, like this exact factor you get, like s times 1 minus s, like but the very nice. Great. And so you can ask kind of like, why does this play so nicely with the special functions you care about? In this and sort of and so the thing I want to say about this is that so the point is that these special functions you care about, they satisfy these types of differential equations. So that implies that kind of this kind of bounds the micro support. The wavefront sets or whatever. Sort of special functions. And in a precise sense, it kind of forces it to be known. So let me explain and so this certainly I need to explain now what on earth I mean. Okay, so for this, let me just recall how you say
It's going very, very far. You won't have time to do that.
give me like 5 more minutes for this and then we'll let me cook. Okay. So just the thing I want to explain is this. Okay, so the point is that H is SL2R modulo SO2R. And then the things you particularly care about are kind of functions which are descended here. For gamma, say it's just SL2. And the point is that so if you want to cook up nice differential operators on this, you can basically descend them from big. You take differential operators on P, which are variant under Lefschin rectangulations. This is just the center of the evaluation, which in this case is just polynomials in this one order 2 thing. And then you take that one order 2 thing, you get to the Laplace. And then just spell out the business about micro support. The one is the following. So you take an equation like this, you know the lambda f this like this equals 0. So the point is that on symbols, all you see is just that the symbol this is the one. This is order 2, this is order 0. The actual item thing. And then so just the geometry here is that you take the cotangent bundle to a group. Let's just kind of take a side, divide it, let's say G times G star. And then kind of you have the moment map. The moment map, just to say, is just the projection. Pick the side. So the whole point is that the invariant differential operators correspond to, you only look at sort of, you further project from G star to G star 1 on G. And so saying like Casimir equals 0 at the level of symbol, things Casimir equals something at the level of symbol becomes Casimir equals 0. What happens when you look at the pre-image of this? You exactly get this no clothing. So just the intuition here is that, like, invariant, like basically micro support bounds saying that you're no potent. Informally, they should just be coming from like, there should just be some differential operators just coming from the group. And coming from sort of invariant, coming from center, some from belt and algebra. Like, they're the things that are producing all these bounds in the mind. And so, and now let me just say one last thing, kind of great, is that, because again, we said there was something about the R setting which is different from the classical setting. The point is, in the classical setting, like, you have to actually construct this and then say, look, it satisfies the. Yeah. The whole beauty of D modules is that, like, this just is a D function. You can just say the differential equation, and that's it. You don't have to produce any solution. That's basically, that's kind of the idea of the extra thing you can do. So it's like once you just know how to write down good sets of differential equations, that's just, you're just producing the model. You don't have to solve it. All right. Okay, that's all I wanted to say about these things are general things. So now let's specialize all to our settings.
You can just push up this blackboard with this beautiful equation.
Oh, okay. Great. Well, wonderful. Okay, so
Beautiful.
If I just try to turn this into a mathematical statement, like I get functions for the Laplacian satisfy an elliptic equation, so they're smooth. Like these modular functions are, so they have trivial microsupport, which is a measure of how non-infinity is. How something is more like a function than like a distribution.
so yeah, I think
These are functions, but because they satisfy these differential equations, but it's not, it doesn't look like null coding system. It looks like zero microsupport.
Exactly what we should look at.
It's exactly what we should do.
yeah, okay, that's fine.
Yeah.
Let's move on.
That's something at infinity, if
Yeah, okay. Well, all right. Great. So the basic thing you want to do is now the point at infinity becomes 1 point from the curve. And so the idea is that so we can make sense of it again. So there was kind of K of X, no of X. And again, this thing was just, if you pick the coordinate, this was just Laurent series, and this was just Taylor series. And so what we want to first ask is kind of similar that there's a map from this to H. You can just take the loop group of the point and map the bun G. It's like making, one condition function. And for example, for in good situations, like if your group is semi-simple, like this type of map is just simple.
if you want to write Bungie as a double quotient.
Yeah.
I think that's correct, yeah.
So example, so if well back here, so in general, so one bungee is it's if you take Okay, you can generally use like finitely consistent functions, but that's good. And then, then you have to sort of keep track of like, what if I change my transition function, if I change my basis inside the disk, and then if I change my basis outside the disk. That's kind of rational functions. So the basic idea is that 1G is some sort of double quotient. And again, like the easiest way, if you want to produce like nice differential operators on a double quotient, like you can just start with just binary differential operators on everything. They're good, they'll give you stuff. And again, you want to say again, the bi-invariant differential operators here will just be the center of the development operator. So that's what we should look at to produce the differential operator. Okay. Sir?
Oh, it's not one with 1G, not yarn.
They're really interesting.
Yeah. Thanks. Yeah. Okay. Great. So,
Gurbir, you have a whole, phase of waiting.
I think it's just dark.
It's fairly light in the morning. It's just late today. It's
Yeah.
yeah, it's good.
Maybe I need glasses. I can't read this. Okay.
The first row thing.
Okay, so here's just a definition. So G of kx, that's just the Lie algebra. This loop group. And so concretely, it just looks like G tensor with I want to is B. Just with the point lines. Bracket. Right. And so we want to say the following things. We want to say like when we take the center of the enveloping algebra of this. Yeah, we want this to be big. This. Okay. Then there's a question of kind of how big should we want it to be? Let's just see an example. So actually, first of all, before we even get to the example, let me just recall that this was G is just again finite dimensional without the group. Okay. And so let me just recall. In this case, the center of the enveloping algebra for G, how big is it? It just looks like sort of functions on the dual of the carbon modulo the Lie group. And then let me just remind you, just to kind of orient us with what will happen later. Again, like you're being fancy, that's the Langland's dual carbon. And that's the same thing as saying it's functions on the semi-simple conjugacy class individual. Okay. And just but even more concretely, just the and. Okay. Now let's just check for GM what happens in this thing.
All right, one question.
Yeah.
Just to make sure I'm still following the logic.
Yeah.
I want it to be big because that's sort of what we expect the space of differential operators with certain equivariance to be, and we want to construct those.
Yes, that's exactly right. Yeah, it's really kind of like these things will for free give us clever differential equations, just nice differential operators in 1G. So we want lots of them.
The more there are.
The more there are, the better. That's okay, so G is GM. In fact, we need to be slightly fancier. Suppose G is the force. then kind of. This thing is still just viewing. Still putative. So let's compute. What does that mean? What's developing algebra is. Okay. So in this case, the developing algebra that just means similarly viewing. Okay, so that should just mean functions on the dual of this vector space. Okay, the whole point is that what is the dual of one? So you take functions at a point, and you take sort of one forms at the same point. There's map to C, which you can take function in a one form. You just take the residue, and that's like a surface pair. Basically, the point is that e to the n is dual to e to the minus n and the dual to so. Okay, so what this is it's now just functions on we check. Let's go with omega 1. This is just functions on e-check connections. Okay, so at least there's some chance that these centers will have some sort of description in terms of connections to the dual. And this also gives us a sense of the count we want, which is that it's the point that for GM itself, just the center is just polynomials with one element. You wish it's just the actual other vector field itself. And when you take its loop space, kind of now the center basically for every we had basically one element in the center before, now we have integers for it. And it's basically it's kind of so the precise thing we want, which is this thing, if it's approximate size, you pick a coordinate. It should just look like the loop space. Yeah. So just each central element we had before, and now we've got all of them. So this turns out to be true. That is the theorem of vague differential we'll learn about later. Let me just write down one more example for you. To see if some sense. So for SL2, so before there was kind of, well, before it was kind of the center was just say polynomials in this one thing. So this was kind of for the finite dimensional thing. So now kind of the center for the affine thing it's basically polynomials in the analysis. That one element kind of splits into like integers many elements, which would kind of get looped. And let me just tell you roughly the formula. So I'll write the formula on another book.
Wait, you guys had a complication.
With this?
Yeah,
So
is this like
yeah, so the beautiful thing is that in general, connections are coarser over one forms. If you have connections on the trivial bundle, it's pointed, but you can talk about the trivial connection on the trivial bundle. Okay. Okay, so let me first give you a wrong formula, and then we'll fix it. Okay, so delta was, and it's the exact formula that doesn't really matter for us, but I just wanted to show you just so you get some feeling for what the type of things are. Okay, this is the usual formula. And so let's try it. Xn just a short name for x and z. But then if you point at delta n, what it's going to be is I'm going to first write it incorrectly. So okay, so it's basically what we expect. There's a slight problem, but this type of operator, if you have it capped on something, big infinite sum, and typically actually won't converge. So you actually have to with the slightly reordered terms here. Or just mostly what it means. So and Im, that just means and you kind of you try to just swap high frequency modes to the right kind of map first. Okay, but it's a beautiful formula. But that's the sense in which kind of it's for each sort of Casimir you have for the finite dimensional group, it in some slightly clever way, let's give you a whole bunch of Casimirs for that. Great. Okay, so that's all I want to say about the center for now. And now let me tell you about what modules we want to compose. Yeah.
So that's all happens to the best in calculus.
Correct.
Are we taking them for extension model?
Absolutely, I'm just saying. What's up? Yeah. Yeah, so a technical point with calls with end is that to literally make this work, you have to pass a certain central extension, really. I think at first pass, you can just pretend that's not there. This is like only one central extension to pick. You get used to the subject enough, like that central extension becomes the zero extension. Okay, great. Okay, next. Go to which model? Use. And again, for this, we look at the picture kind of. There was SL2R, mod kind of the clever subtle arithmetic bit, or like the sort of the global bit gamma. And then there's kind of the local bit, which was K. So 2 of R becomes the maximum function. And so the rough idea is that it's kind of read it as this modulo this. And so the types of systems of differential equations you want to use are kind of, you use the Lie algebra of SL2R, but there's be something about equivariance. Okay. So similarly for us, since we have e of kx mod something, which is kind of with the gamma, and then we mod out on this side to G. The point is that this is the side which tells us like the systems of generating relations we want to. Okay, so definition KL the category of modules for this on which. So it's kind of. But in general, right? You know, if you have a representation of a group, you can differentiate to get a representation of the algebra. You can't always integrate that, right? It's something like developing algebra for the algebra, and there's a left translation that doesn't integrate with that. And so the idea is that kind of it's okay. So these are modules for G of Kx, on which sort of the action of just arcs. Yeah. No, they're definitely not central or critical. Yeah, sorry. Okay, so sorry. So for people who know this stuff, when I'm talking about SL2 without a central extension here, it actually means that critical level. Okay. Okay. I'll say this at the end. Yes. Okay, so we want to consider these types of models. It's like something like a category O or parabolic category O. If those words mean something. No, it's okay. Great. So let me tell you some basic objects in here.
By the way, superfly can be integrated as an operator.
Great question. So I was thinking about the Dhillon category here, because absolutely it's just a property, not a structure. On the drive category, it's a structure. Yeah. So yeah, if you wish, it's great. Yeah, very good. But also, I should say, up to unimportant renormalization issues, these things are also drive categories. Of course, it's not really. Great.
What does KL stand for?
Hashdan and Lustig. They prove lots of great things about.
Does publish this very
Great. Let me just give you some examples. Yeah. Okay, so here's. Okay, so suppose you take suppose V is just a representation of this group. Yep. Then what you can do is you take the induction from just the Lie algebra of this. So the Lie algebra is the full thing of V. So the point is this by itself, it had an action of this group, but there's no action of the larger Lie algebra, right? You just fix that by just inducing it. Okay. So this is an object. And in fact, sort of for V finite dimensional, these inductions are system compacted. Okay, let me sort of specialize this. Moving on. So if lambda is the dominant weight, V lambda kind of the irreducible G module that highest weight, then the point is that it's so there's some sort of parabolic induction diagram. Basically, I can take this representation of the finite dimensional group, inflate it to view it as a representation of this arc group, and then induce it. This is by definition, this is induction from with OX, U of KX, which is V lambda, and we call it the bottom. Um, And one very special one. V zero is which is called the vacuum. Point that you'll learn why it's very special. Okay, great. So let me next tell you. So actually, first, so these are kind of some basic class of objects we can care about, right? So there's the category of all these things. But then there's basically just this explicit type objects, they over dominant weights, and then basically this category.
I have this slight concern that there's a question about what the definition of KL is, like what it means for the month for
Great.
Great, and then
Yes.
it's right for us.
Okay, yeah, so let me give you. Here's just an example. Yeah, but let me explain it. So let me give you an example for just finite dimensional game, right? So suppose you have GM acting on, let's just say L, a one-dimensional vector. Right? So in this case, kind of, if you differentiate the action, then the Lie algebra generator, it just acts by propensity. Right? I just wanted to, you can't get like, so you get a one-dimensional representation of the algebra, but you don't get a completely arbitrary one. You get one in which the generator of the algebra acts on you. Whereas, but like sort of saying TDT acts by like any lambda in C, that defines a representation for the algebra. Which doesn't integrate. That's the sense in which, like, for a given group and it's the algebra, most representations of the algebra don't integrate back to it. Okay, and that.
So okay, so here you're explaining what it means for a representation of the algebra to integrate to a group. Yeah, that's what you're saying.
Yeah.
Great. And then maybe also the reason that, just thinking to myself, the reason that you were giving these examples to explain what KL means, one thing you can say is that what's an object of KL is maybe a quotient of one of these file modules, or it has a finite composition by some of these file modules. So that's what you're saying about compact generators, is in some sense, these modules are the sort of defining objects of KL up to things like quotients and extensions and maybe infinite direct sums or colimits.
Yes, thank you so much. Yes, exactly. So yeah.
So this is something about one systems on GM.
This?
Yeah, so honestly, I still don't understand what it means to integrate in the same.
So if you have a representation of the group, you can differentiate, you get a representation of the Lie algebra.
But not every representation of the algebra comes from a representation of a group.
Okay.
So integrate means to extend, to lift the representation of a Lie algebra to a representation of a group.
Okay.
Right. So there's something confusing, which is if you have a simply connected semi-simple group, then every finite dimensional representation does integrate, but you already run into issues for PGL2 or greater thing for GM or for GA, there are issues. So it's a sort of a property in current context of which representations actually integrate. And this group G of O, it has some part which is maybe essentially, it's like a G, which is essentially a semi-simple simply connected group under some hypothesis G is semi-simple simply connected. But then saying that G of O integrates means that the act locally no.
Yeah. Like, should I write that down? Okay, yeah, just so there's no history, it's like,
But that's concretely what it means, it's like.
Yeah.
If G is reductive, there's a little bit of a condition, like in this example, about the integrality of something. G is like an adjoint group or something, there's again a little bit of something should be something, not something. And then there's a little bit of
Yeah. Great, so yeah, just to repeat what's been said, so it's, let's just start with, let's just say an object of the Dhillon category. So it belongs to KL. If and only if the following things happen. So if I take x n's, n greater than 0, these act locally impotently. So it is that these exponentially, this is sort of first congruent subgroup, that's probably impotent. We want to see sort of nilpotent for the actions of the algebra. And then so that's kind of positive modes. What about zero modes? So the idea is that then kind of the condition you want is, so if you wish for, okay, so let me just first tell you, so if G is semi-simple, simply connected, you just want if you just take sort of random vector and you act on it by just the zero mode development algebra, you want this to be finite. And sort of when G is a torus, it's basically this kind of integral eigenvalues condition. In the previous example. And then the general case is just a mixture. All right, great. So the next thing I want to tell you about is kind of so let me first say it kind of in maybe down to earth language, which is when you play with these Weil modules, there's the following beautiful thing. So here's a beautiful fact.
How much it looks like being like in KL is a problem.
Yeah, a Dhillon category.
So like what's the actual stuff you want like
The actual version of what?
of like KL? Like you need actually
Okay, so there's like a million different definitions. One is just literally say, take just the naive derived category of this, take the full small subcategory generated by the Weil modules and complete that. That's one definition. There's another definition, which is in the same way that responds to the question about dualizing sheaves. So there's some notion of the appropriate renormalized derived category of all modules for this. That is in categorical action of the loop group. We take G of invariant. That's the same. Okay.
So why taking GFO invariance of the category of the algebra representations corresponds to the definition of
Integrated thing. Yeah.
Ah.
Which is using why does that actually just mean integrate the action?
okay.
That's the question?
That was the question, yeah.
Yeah, great. It's no, we go back to you. Okay. Yeah, so the point is like, let's see if I can say this properly. So okay. Okay, let me say super formula. So you have this V with some action of this. And then this equivariance thing that you think of giving you basically tell you is a representation of this group. Just the underlying vector space of it. Okay. And then as you can imagine, there's some compatibility between these. And the point is that, so in fact, in this world, you can talk about weak equivariance and strong equivariance. So the notion of being weakly equivariant would just mean that kind of the action of this commutes past the action of this in the way you'd expect. When you pick up a conjugation, the condition of strong equivariance actually means like not just literally derivative of this action that covers just the action that arcs of algebra. Yeah, so
this is like a demo construction, right? This is kind of a DK module, maybe
exactly. The classical notion of a GK module is the same as just like you take a K strongly equivariant object and just G the algorithm.
This was sort of my question, like, yeah, at the beginning you promised something that didn't have a classical analog. And then you convinced me that classical analog is GK module.
So no. So again, so the thing which does not have a classical. Okay, so well, Dennis and Sam had stronger objections to this, but the thing which doesn't have a classical analog is like I can't write down a modular form by saying like nabla minus 3.
Okay.
Or delta minus 3. Yeah. Right. That's the step which doesn't have it.
Okay, and that's the only sense you were.
That's okay, I can say more about this later. Yeah. That's some of Bailenson, Bernstein, Lutz, some beautiful stuff. Okay, so now here's the beautiful fact. Okay, so suppose I take V and W, two finite dimensional GOX modules. So the first statement will not be very surprising. The Hom from V to W is the same as Hom from W to V. Or sorry, it's Hom from W to W. You just take the dual representation. Okay. Now let me say something which will seem weirder. Okay. The beautiful thing is that this is still true for the induction. Now, I want to be very clear about it's you're inducing the dual, that's not at all the same as taking just the naive dual induction. Okay. So there's some sort of kind of cool thing happening here where like there's a duality on these types of representations of this Lie algebra. It's something cleverer than just taking the contribution of the finite inequality. It's like somewhat doing that after the induction. Okay. And so you can ask, like, what on earth is this? And so, okay, so that's kind of the most down to earth way to say it. For this conference, we know that if you have a category, and the set of compact generators comes with some whatever involutive anti-equivalence, that's the same thing as saying the category is self-true. Okay. So in other words, this is what this is coming from. This is coming from the self-duality of the category. This comes from.
Sorry, you're always guaranteed GOX. Is that the same as OXG or OX plus B? Or is it actually just looking for?
Sorry, this is exactly this.
So it's not a point.
It's not what?
It's not its first group, it's a group set.
Yeah, it's a group. Exactly. Thanks. Yeah, but this function of self-duality, the KL is seen as KF. And let me tell you what the pairing means. So if I start with two modules and n, so I need to come up with vector space. So here's what you do, so, okay. I can literally just tensor them. That's not gonna be quite good enough. I need to make that smaller. And so. So, let me first say, informally, like say, if you're doing with representation of say like a finite group or something, the duality would be you tensor the things, then you take invariance. Okay. Or go to the finite dimensional algebra, it's like, oh, okay, invariance and the algebra come on. But the idea is that here, there's just one reasonable notion, take invariance. And this is something called sending from. In fact, I encourage you to ignore all the details of this. Okay.
You want to write it so small that we can't see it anyway.
Yeah. Okay. So just let me just put the words on the board. There's something called relative semi-infinite homology. But like literally the way to read this is like there's only one reasonable notion of like variance in the setting. This is like you do that.
I heard the member of the audience asking, is this more like homology or more like Kac-Moody?
Who asked that? Was it
I can't just go.
what a great question that is. All right, great. So yeah, let me just say
Also, maybe immediately.
yes.
Is it the same as form from this problem with this problem was it will.
Yes.
Yeah, okay.
This is okay.
Wait, sorry, what was the question?
I don't know. Is it the same as form from
Like this would be the thing, just on to the back of the next part.
Okay, what's written is semi-infinite homology.
that is a form
I'm
from
showing the vector representation or GMO invariant.
So you're I'm
Oh,
sure
semi-infinite homology, as presents this question, differs from that by you sort of first do GMO.
Yeah, sorry, that's happening. Yeah.
Invariance.
Yeah, so that's
Sorry,
like that's happening.
Yeah.
I'll say yeah.
Yeah,
So
but,
two steps. The first step is what you said,
okay.
and so that's so to speak. That's what you think about this part of it, and then you sort of do something about the rest of the reality. And also, yeah,
But this, whatever. What's the symbol and what's also the first symbol in this expression?
okay. All fair questions. Okay, let me. Okay, here's. Okay, C is for cochains of some sort. Then there's an infinity divided by 2. We'll see where that comes from, so they're not a big deal. Kind of ignore it, then there's like a star, basically it's cochains of some sort, maybe group invariants, the algebra and something. Okay, so. And then it was kind of, so the whole point is that like, so another just basic fact of life is we're ready for like GM. You take group invariance for GM and representation, or if you differentiate, you take like the algebra invariance. So like in the Dhillon categories, it's the same notion. In the derived categories, it's the same. Okay. So the basic idea is that like, so because we're in this kind of Goldilocks situation, we're like halfway in the algebra, halfway in the group. We need to take some notions of invariance to kind of keep track of that. Okay. And that's the thing of there's a notion of relative. So in the finite dimensional case, you have a relatively algebra homology with like a subgroup. But here it's the same thing. There's kind of just like plain vanilla semi-infinite homology, but there's no group there. We're talking about the KL categories and we need the group there. Okay. And so kind of so here's an informal definition. It's kind of its first group homology. along G of OX. And then two, it's kind of, then you do Lie algebra homology. Along what's left. So, let me also just remind you that for like a finite dimensional Lie algebra homology, Lie algebra homology lives with homology of this determinant of this cohomological shifts and twists like character, they're exactly the same. Okay. So like the I have like 10 minutes, 5 minutes, or 5 minutes. Oh, fun. Okay. Let me not say more than this about the definition. I don't think you really need to know very much detail. Okay, so the last thing I need to tell you about is so there's something called the Greenfeld so-called product. Actually, sorry. Let's say just one last thing about this, and then we'll be done with it. Just the intuitive picture for this, which I won't really say super carefully at all, is so just if you like half remember what Hamiltonian reduction looks like, there's two steps in it. Like a moment math condition, it's setting something equal to 0. That's this, and it's like you're taking a fiber that's into a tensor product, and then you're taking the group invariance in that fiber, and that's
It's like, oh, it's a bunch of, like.
But
Do you oppose all ideal and do? Like,
yes, absolutely. Yeah, this is yeah. Okay, the DS reduction. So what's the idea?
So one absolutely essential thing for people to know is that there's really, again, another central extension here, which isn't the central extension that we were talking about before, but in the case of this productively algebra, is twice the central extension we were talking about before, and that's.
Yeah, so
Yes, so in some sense, this couldn't have been a precise definition because it didn't have a central extension built into it. And if you want anything like a precise definition, you would have to absolutely say.
Yeah. Absolutely, yeah.
So do you not question about the central extension?
Do it.
Do you not question about?
If you ask as a question at the very end, I'll say something right. Okay, Greenfeld circle of reduction. Okay, so what's the idea? So it's kind of an amazing thing the first time you see it, and the good news is the first time you see it, you can see it in the affine phase. Let me tell you what it is in finite dimensional phase, and we'll worry about it. Okay. So first, just the orienting statement is like in some sense, like the basic, I don't know, dance or whatever representation there is. Like, a group isn't exactly the torus not the vowel group. It kind of is, right? You often fight very hard to make that. And so, right, so torus not the vowel group shows up in this picture first as like a sub algebra of the node. But there's something great where it's kind of the point is it's a sub algebra. But also, okay, and I'm going to put this in quotes. It's also kind of a quotient. And this quotient is in quotes because precisely it's again a Hamiltonian. then we write, again, Hamilton reduction, you actually write it down, it's like some sub-quotient thing. But morally, that's the cotangent bundle of something on the actual thing, you're just modding out. Okay. That's kind of quotient and some flexible. Okay, and so how do you do this? So let me just show you. Okay. For example, suppose GLN, and like this picture was kind of the same. You think of it as the subalgebra, but saying the way your brain normally thinks is G star maps down to G star level. Okay. So the claim is that there's canonical lift back. Let me tell you what that is. So that S is the following sort of classical story, which is just like if you take a companion matrix, right? Like it's you run over just matrices like this, like they're in one-to-one bijection, which is characteristic polynomials. Okay. And the idea is that like you want to say this in a way that makes sense for every the algebra. So you stare at this and you say, okay, this part looks pretty familiar, right? This is like, this is the F in principal SL2. Like, and then, you know, if you're being super, like, we were talking before about these Whittaker characters and they were like some entries alongside the just below a diagonal, just above a that, right? The same type of thing here. So, yeah, well, it is a kind of right now we're writing it as a sub, but in fact we should write it as a sub quotient. Let me write that. Okay, so the thing is that so when you take just companion matrices, these include into just F doesn't mean just in there. And then okay, I want to take F plus E modulo something, make this composite for my thing. Okay. So if you just dimension count, the thing you want to probably modify is 10. Okay. The force is what's left, and the force will split there. Designation. So that's yeah. So so just in the finite dimensional case, here's the definition. Yeah, so there's kind of so there's going to be some functor from representations of the algebra. The a priori just say vector spaces, which is kind of it's you just restrict your representation to n. Two, have to do with a generic character. Completely could be thrown along this diagonal. Okay. And then three, take sort of the algebra. Again, you could say, should I take homology again, it doesn't really matter up to shift, whatever. Twist, so it's like In fact, even here the twist is trivial. Okay. So, so in fact, you enhance to something not just vect. In fact, you'll factor through modules for well, in fact, let me just say so let me just say something. But this thing is the same thing as following from the induction from N to G outside U. So you're naturally a module for this algebra, whatever it is. But then the delightful fact is that this is just the same. The point, this is the sort of this is the kind of quantum Hamiltonian prediction. So again, it's this is quantized in the statement that this thing magnetized quantumly to G1. Okay, and so there's this very pretty picture that kind of getting just this kind of E mod W and purely Abelian game.
You're over time, so you.
One minute.
Yeah, that's great.
Yeah, it's good, it's good, it's good. Okay. So the last thing to say is that so instead that you can just copy this in the atom. Okay. So now it's kind of the DS reduction is the function. Now we're taking again the only homology theory we have around. Now we're applying it to sort of loops into our thing. And now, so this is now okay. This is the derivative. Of the character from Andreas is thought. So this is some thing, let's say, you don't even have to start with KL, you can start with just any Kac-Moody modules. And it cuts them down to kind of produce a vector space. And so the rough picture, by the way, is that like in the same way that Sam said that like the Whittaker sheaf is some like clever non-abelian adaptation of just delta D modules. The point is that again, like it's sort of so let me say it here, which is that you start with your module for your confusing non-abelian thing. You want to get to kind of the homeland vowel group Centauri and nothing else. And the way you do it is you take the module and you like kind of just take some brutal shadow. Okay. And sort of many theorems in representation theory of the fact that taking that brutal shadow actually doesn't destroy any information. And you're going to learn a lot of those relevant types of statements in this setting and the rest of it. Okay, let me stop you. Yeah.
Where I focus on the motifs with induction was not or yes.
Yes.
But what about that type of extension? Okay, if we can't do it now.
Okay.
He said no. Yeah. No, I will not. Ah.
Okay.
So let's I'm afraid you will have to do it.
Okay. Yeah.
Sorry.
Okay. Okay. Thanks. Yeah.
We'll do it again.
In 5 minutes.